So in this problem, we're starting to think about a different kind of transformation, right? Where I'm using multiplication instead of addition and subtraction to change my function. So if this is the graph of y equals r of x, and if I want to know what the graph of y equals 3 times r of x looks like, then what am I acting on here, the y coordinates or the x coordinates? Y equals 3 times r of x. In my equation, if I were acting on the x coordinates, I would be replacing the x inside of my function with something, 3 times x, right? But here my 3 is appearing on the outside of my function. So it's really not acting on the x coordinates, it's really acting on the y coordinates. Another way to think about this is to think of it as being the same thing as dividing both sides by 3. We could think of it as this instead, 1/3 y equals r of x, right? Here we can see it's acting directly on the y instead of acting on the x, but it's the same thing as that, right? And so what am I doing? I'm taking the y coordinates of all the points that I know, and I'm multiplying all those y coordinates by 3. So if I know that -2, -1 is on my original graph, what point is going to correspond to that point on the new graph? Yeah, -2, -3. I've just multiplied that y coordinate by 3. Right? Multiply the y coordinate by 3. And that gives me the point on the new graph, right? So as you think about what happens as you multiply all the rest of the y coordinates by 3, you should see the graph of your transformed function begin to emerge. And another thing to think about, too, is which points on this original graph are actually not going to move when I multiply them by 3. So equally important to what changes is what doesn't change. And when I apply a vertical stretch or a vertical compression to a graph, I'm multiplying the y coordinates by 3, and the points that don't change in that process are the points that had a y coordinate of 0. So all of the x-intercepts on my transformed graph are going to remain the x-intercepts of the original graph. So all those points that began on the x-axis are going to still be on the x-axis after we perform this sketch. So that's just a little consistency check after you draw the rest of your graph to make sure that it is hitting all the same x-intercepts as the original graph did. So the first thing that we were asked to do was think about what does the graph of y equals 3r of x look like. And that was the one, again, where all of the y coordinates of the points are being multiplied by 3. So -2, -1 gets stretched down to -2, -3. All of the x-intercepts, because their y coordinates were 0, the y coordinates are going to remain 0 when we multiply them by 3. So the x-intercepts aren't going to move. Everything else is stretched away from the x-axis by a factor of 3. And so it looks like the graph gets taller, right? Y equals 3 times r of x looks 3 times as tall as the original graph. Meanwhile, y equals 1/3 r of x, the opposite happens, right? Again, because we're multiplying the y coordinates by something, all the x-intercepts are going to stay the same, right, as they were originally. But now my y coordinates are shrinking by a factor of 3, and so I'm compressing this graph in towards the x-axis by a factor of 3. So there's y equals 1/3 r of x. And again, we keep track of the fact that this is a vertical stretch or reflection by the fact that what's happening here to these equations is really something that's happening to y. It's not happening to x, which is sort of on the inside. It's the argument or the input to this function. What's happening instead is happening to the output values. So it's something vertical rather than something horizontal. As we move over into the graph of the s function over here, I want to look first at y equals -1/2 times s of x. Because what I ultimately want us to be able to do is to get all the way towards this sort of multiply transformed equation, y equals -1/2 s of x plus 2 quantity minus 2, right, where it has a bunch of different transformations done together. But if we just look at the first step, y equals -1/2 s of x, what would you say is actually happening in that step? First, it's reflecting over the x-axis. So let's sort of think of this as a combination of 2 steps. The first being, we're going to replace s of x on the right side by minus s of x. And so that's reflecting. I would call it a vertical reflection, or a reflection across the horizontal axis. And so if we just did that step, we would end up with a graph that looks like, let's see, how would I sketch this. It would go like that. Right? If I just did the vertical reflection, I would end up with this graph right here. And that is y equals minus s of x. But then what's happening after that? It's being stretched how?
By a figure of 2.
By a factor of 2, yeah. In which direction?
Horizontally.
So on this graph, what it looks like, so take a look at how this point on the original graph is related to this point on my transform graph, or this point on my transform graph. What's the same about all those points? What do all these 3 points here at these corners have in common?
Same one.
They have the same,
Same X.
they have the same x value, right. All the x values are negative 2. X equals negative 2, x equals negative 2, x equals negative 2. But the y coordinates are all different. So that indicates, is this a vertical or a horizontal transformation that's happening here? So the x's are remaining the same, the y's are changing. So this is a vertical stretch, or a vertical squish. I'm going to call it a squish. Right? Because we've taken this black graph and we've squished it in towards the x-axis by a factor of 2. All the new y-coordinates are 1/2 of the original y-coordinates. Right? So the whole thing gets kind of shorter as we compress it in towards the x-axis. So this negative 1/2 out in the front here, we can kind of think of as 2 transformations stuck together. The first transformation being a reflection, that accounts for the minus sign, and the second being the squish that we get by multiplying by 1/2, right, on the y direction. So then what do I need now to continue this process towards the final answer that I'm looking for? Okay? What is this missing that my final transformation is intended to have? So what's missing here are 2 shifts. One of them that's happening directly to the x variable, and the other one that's happening kind of on the outside of my function. Which order should I do those in?
Doesn't matter.
It doesn't matter because shifts commute with one another, right? It doesn't matter if I shift horizontally first and vertically second, or vice versa. That choice is completely our own to make. So let's suppose that we do the vertical first. Which part am I talking about here?
Outside of the...
The outside, right. So I'll do my minus 2 here on the outside, and that's going to have the effect of doing what? What kind of a shift is that? Vertical, which direction? Down. So it's happening on the outside, so it's happening to my y variable, and because it's happening on the right side of this equation, it's happening intuitively, right? We're shifting down 2 because we're subtracting 2 from all of my y coordinates. So at that stage, I would have moved this graph. So take any of the y coordinates on my original graph and just move those y coordinates down by 2. So I'm going to get something that looks like, see if I can get a good sketch here. Something that looks like that. All right, so I've just taken my red graph and I've moved it down by 2 units to get this equation. And then what's the difference from here to there? Replacing x by x plus 2, what effect does that have?
Shifts it left.
It shifts it to the left by 2. Very good. It's horizontal because it's something that's happened directly to the x. Left. And it's counterintuitive because it happened directly to the x, right? So adding 2 to the x variable achieves a shift to the left by 2. And so at the end of the day, I'm going to draw our final answer here in green. I'm just going to take all of these points and I'm going to shift them over by 2 units. And I'm going to get a graph that looks something like that, right? So this green graph right there would be the graph we're looking for the final answer. Okay. Let's think about what would happen if I did the shifts and the stretches first. The shifts first and the stretches second. So starting from my original y equals s of x, let's say that I want to shift this thing. Let's do the shift down by 2 first. So if I shift it down by 2 first, what's the new graph that I'm going to get is going to look like this. So it's going to come kind of like that. And what's the equation of that new graph going to be? If I shift down by 2. S of x, yeah, with the minus 2 on the outside like that. Okay. And then let's shift it to the left by 2, the step that we did last over here. If I shift it to the left by 2, then it's going to move over to my new corner is going to be down here. So my new graph is going to look something like this. And what's my formula going to be? Y equals yeah, I'll replace my x by x plus 2, minus 2, right? Okay, and now let's go in and try and let's do our first reflection step here. What do I need to do to reflect this thing vertically, reflect it across the x-axis? Put a negative sign where? Vertical reflection. At the beginning of the function, right? Replace y by minus y, or equivalently, replace this whole right-hand side with the opposite of the right-hand side. So what's going to happen when I do that? Y equals minus quantity s of x plus 2, minus 2. I'm going to take this red graph, and I'm going to reflect the whole red graph over the axis. And that's going to bring the vertex, this little corner, it's going to bring it all the way up to here-ish. My y-intercepts are not going to change. Well, now I'm going to kind of run into my own graph there. But it's going to look something like that, right? Take the red graph, reflect it upwards. But what's going to happen here, and do you see what's going to happen in this algebra that we didn't expect to happen? If I slap a minus in front of the whole right-hand side, what happens if we distribute that minus? We're going to get minus s of x plus 2, right? Which we kind of wanted, right? But what else are we going to get? Yeah, this minus 2 out of the end is going to turn into a plus 2 instead. And so if I just rewrite this expression to distribute that minus, this is what it's going to look like. Minus s of x plus 2 plus 2. And why is that bad? Because what is this plus 2 doing now? It's not moving it down like we wanted. Instead, it's moving it up by 2 units. And so that should be kind of a red flag for us, right? This plus 2 right here indicates that so something happened along the way that we were not expecting to happen, because we were trying ultimately at the end to get a minus 2 to shift downward by 2. So what is a way to make sure, so first of all, let me just pull this all together into the following statement, that even though all the shifts are commutative with one another and all the stretches are commutative with one another, their shifts and stretches are not commutative with each other. It matters if I shift first and then stretch, or if I stretch first and then shift. Generally, I get different results from those two things. So what's the best way to keep this all straight? What did we do over here that we didn't do, or we did differently over here, that can help us to make sure that we don't get caught by this kind of thing? What's a general principle that we could keep in mind? That's sort of the genesis of your question, Jake.
Just go left to right?
Well, I would say left to right. Yeah, let's go with that more general statement, right? Depending on it, there won't always be left to right necessarily, but the stretches and the reflections, all the multiplications should happen first, and all of your additions and subtractions should happen last. Where else does that tend to happen? PEMDAS, exactly. So follow PEMDAS when you're thinking about graph transformations that involve stretches and shifts. So always think about your shifts and your reflections first. That's the M and the D, the multiplication and division. Shifts and reflections first. Stretches and reflections first. If only they didn't both start with S. Stretch first and shift last. That will make sure that you don't get caught by this lack of commutativity in the two types of graph transformations. Save all of your shifts, your addition and subtractions, until the end of the problem, and do all of your stretches and reflections first.